just makes me laugh. Sounds like a click of a gun.
All right, and let's see where we left off in our code for our operating system simulation. Okay, so last time, whenever we create a PCB, we'll start its process state as new. Generate a random number. Generate a number of lines of code between 100 and 5,000. Spin through, fill it up with lines of code. So lines of code will either be I/O, or it'll be move a literal into a register, or move one register into another register. And registers are going to be, our fake CPU here has 4 registers. Okay, so register will be either 0, 1, 2, or 3 for our 4 different registers. And these lines of code are going to be interpreted later by our CPU that we're going to be writing. Okay, so we have this dot process state is a byte. New state, did we make these bytes? We did. Is it not like us using new? We've had this before. Let's write this. All right, so it's okay with that. So we're going to say process. Oh, was it?
Yeah, but it's just usually wasn't saved. Should go after.
Yeah, that's okay with that. Okay. That is the same thing I had written there a second ago, isn't it? All right, well, it's okay with it for right now. Program's counter starts off at 0, very beginning of the program. Process state then moves to ready state, keeping in mind that this idea of a process getting loaded into memory, where fake loading into memory can take some time. So for our little example here, it's going to happen very quickly, but in reality, it can actually take some time. All right, then we have our little display method, which shows the process state, which should always be ready for these when we display it. Code length, number of lines of code, and program counter, which should be 0. And this is going to be of interest to us when we start running this through the CPU and our program counter starts changing, and our process state may also change. Okay? Now inside of driver, so we created one process and then told it to display itself. And I think if I remember correctly, we kind of had a loop that went through and showed a bunch of processes that they were getting random code lengths. Okay. Now, just to keep going down this path of simulating this, we have these PCBs. So a PCB is the result of double-clicking on an icon, like double-clicking on Microsoft Word, that guy getting loaded into memory and ultimately getting in line ready for the CPU. Make sense? Some programs, they will get CPU time. I don't know if there's a program that can exist that would be I/O before it had CPU time. It would have to get CPU time to hit the very first I/O request. So you'll always be a ready state first. You'll never be in a waiting state first. So we've double clicked on the program. It gets loaded into memory. It gets into line for the CPU, and then the CPU starts. When it gets its turn with the CPU, it's going to start working through the lines of code. Now, last time we were talking about this thing called a process scheduler. So the process scheduler is going to have a linked list of jobs. These are all of the current PCBs in the system, every one of them. Then we're going to have a queue, that is a linked list of all the elements that are currently waiting in line for the CPU. And then device queue, which is all the elements that have left the CPU, and rather than getting back in line for the CPU, they're now getting in line for a specific device. All right. For us, we're just going to treat every device as an I/O device. We have one mini device on the system where all I/O happens, just for our simulation. Where in reality, on a computer, we might have many different I/O devices. Okay. So let's go back to the slide set here. So here's our process scheduling. We talked last time about this migration process as something leaves a queue and enters another queue. That's going to happen as we remove something, dequeue it from one of our queues, gets into the CPU, and then gets enqueued someplace else. We looked at this last time, a process representation in Linux. We were wondering why state is represented as a long. It probably has to do with the register it's being stored in. But in any case, this is a PCB for, well, this is actually a part of the PCB in Linux. So just some real life operating systems code. And they have this thing in here called time slice, which has to do with the CPU scheduler. All right, so we kind of have two elements working side by side here. We have a CPU scheduler and we have a process scheduler. The process scheduler, which would have made a good quiz today, right? Maybe, but whatever. The process scheduler is in charge of keeping track of all the current processes in the system, all the PCBs and what they're currently up to. The CPU scheduler is in charge of context switching, moving a process into the CPU, moving a process outside of the CPU, and ultimately working on an individual process. And keep in mind, as our CPUs get more and more complex, dual core, quad core, multiple CPU, physical CPU machines, as that CPU scheduler gets more complex, we run into this problem of that CPU scheduler becoming more complex. How do we schedule jobs for the various cores in the CPU? Now we can have more than one thing happening at once. We can have 4 things or 8 things or 12 things happening at one time. And with hyperthreading, sort of kind of 24 things happening at one time. All right, so this might be what the ready queue looks like. All right, so ready queue has it's a linked list. So we have the head of the list, which leads to one PCB, which leads to another PCB, so on and so forth. All right, here's some different I/O devices here. For our example, we're just going to let's pretend like we just have this one since there's actually things linked to it. So we have this single I/O device called disk that has PCBs waiting for access to that I/O device. Okay, so again, it's just another linked list. And this guy keeps track of a head and a tail, so it's a doubly, well, actually, as they've represented it here, it's a singly linked list. Not sure why you'd need oh, actually, I do know why you need the tail. So we'll ask that question to the group. Why do these linked lists need to keep track of the head as well as the tail? Why is that efficient? And a couple of you who have not had 300 aren't going to be able to answer this yet. So if that's you, that's okay. You want a hint? These are all queues. We have a ready queue, and we have an I/O queue, device queue, whatever. So they're queues. How do queues work? Lots of.
Take from the back, put
I guess depends on how you.
Yeah.
Depends on which end you say.
Yeah.
Okay, you get into line at the end of the line. You leave the line at the front of the line. So we need to know about two different places in the line. To add people to the line, we need to know. Let's just say we add them to the. Let's say we add them to the end, to the tail. We remove them from the front. Just dealing with heads and tails. So when a new PCB comes into the system and they need to get into the queue, we're going to add them at the end of the list at position tail, rather than having to traverse the entire list to get to tail. Does that make sense? So it's an efficiency thing. If we know where the end of the line is and we can just immediately jump there through a pointer, it's going to be faster to add a PCB to the queue. Removing something from the queue is always going to be removing from the front at the head. That makes sense? So that's why we need to keep track of both of those pointers, the head and the tail, to make our queue efficient. So they've depicted this as a generic linked list, but really we're looking at a special version of a linked list that is a queue, which is just a simplified linked list. Because if you remember in 300, when we wrote our first linked list, we had our linked list kept getting more and more complex as we were adding things to the front, which was easy, adding things to the end, which was easy, adding things in the middle was less easy, right? That's when we had to like disconnect a whole bunch of stuff, and then we did the remove methods for removing from the same places. So with queues and even stacks, we've removed that complexity. Queues and stacks we never have to let somebody get in the middle of the line. We never have to let somebody leave the middle of the line. Now, one thing we're going to have to tackle at some point here is as our CPU scheduler gets more complex, as our process scheduler gets more complex, because remember, our process scheduler is in charge of the ready queue. So the process scheduler is the bouncer. They get to decide who goes to the CPU next. Okay? CPU does their job once a PCB shows up. But the process scheduler is that bouncer that decides who gets in. So if that process scheduler who's maintaining these linked lists, our ready queue and our device queue, if they decide to start giving higher priority to certain PCBs than others, well, now we have an issue of, do they sort those queues? So just kind of, we're not going to implement this yet, but just kind of thinking through the list, do we just have important processes and unimportant processes? Where if you have a high priority, we send you to the front of the line? Or is there kind of a pecking order? So let's say you go into McDonald's and let's say there's kind of three different, let's say it's the caste system, like in some of the Eastern countries. Well, this still exists, the caste system, where you kind of have multiple classes of people. So, and I'm not sure McDonald's adheres to the caste system, but let's just assume it does in our example here. So you go into McDonald's and you're a member of the top tier class. You get to go right to the front of the line. Okay? If you're in the middle tier, maybe you get kind of inserted somewhere in the middle of the line, behind the top tier people. And then if you're the lowest people, you're always in the back of the line. You get the front of the back of the line, right? Okay, so if we thought about managing that McDonald's line and the complexity that goes into that, which is just almost as complex as the line at Cops. How many of you have been to Cops Custard here? So you know what I'm talking about. The line at Cops is like the most cryptic line in the world, isn't it? You walk in and they have, let's just round down and say 90 registers. Okay? And above the registers, not directly above the registers, but sort of kind of above the registers, they have signs like, go to this section if you're only ordering this stuff. Go to this section if you're ordering this stuff, but maybe some of this stuff. But don't go to this guy if you want some of this stuff. They'll start sending you to it's ridiculous. And then there's just this kind of cluster, this line, but it's not really a line. You just kind of get into the cluster and you find out where it's feeding. Okay, and then you decide, how many of you have never been to Cops? Let's go that route. It's an experience. You have to go there sometime. Really good custard, first of all. Also very good burgers. But
so what you're saying is that Cops is the DMV burger.
It is. And you see it all the time when somebody has been waiting in line for like 20 minutes and then they ship them to another line. because they tried to order. Like if you go, they have one line that's for let's call it the ice cream only line, but only certain ice cream. If you're either getting just the dish or a cone of custard or the flavor of the day, there's one kind of fast lane for that. But if you want a sundae, don't order it in that line. No, you go over there with the guys who are ordering burgers, which are actually the shorter lines. Because almost always people go there for ice cream. So they get into the faster service but longer line for just the cups or the cones. If you want a sundae, you go to one of the food lines. But if you want just a cup or a cone of custard, you go to the food line, they'll ship you over the other line. It's ridiculous. And those of you who've been there, you can back me up on this. It is like that, isn't it?
Yeah.
It's kind of ridiculous, the lines there. The place is always packed.
Oh, yeah.
Even in the middle of the winter, when you wouldn't think people want custard.
9 p.m. middle of winter, it's still got like max amount of people in there.
Yeah. There's like standing room only.
Well, that's it. To begin with.
Yeah,
There's no chairs to begin with.
that's right.
It's a standing room.
But just for the lines.
Yeah.
But it is a good place. You should go there. The location I go to is just south of Bayshore. Halfway between Bayshore and Solly's. Yeah, it's like the food mecca right there. Hey, hold on, is that? I don't think that's a Christian worldview, is it? Islamic? No, that doesn't fly. What would be?
We'll just classify it as a world.
It's the. Well, no, I need to get a point here. It's like the food Jerusalem. Food. I don't know.
If you find one
Give
more,
me a point.
if you find one more in that region, we can go with the Trinity.
It's like the food Jewish deli. Man, if only there was Jake's Deli there too. And Speed Queen Barbecue. All in that one. Oh. How many of you have been to Speed Queen? Seriously? Nobody in here has been to Speed Queen? How many of you live in this area? Are you
Never
serious?
heard of it.
Oh my gosh, Speed Queen is probably it's always rated the best barbecue place in Milwaukee, but it arguably is the best barbecue in like the Midwest. It's really, really good. And it is in like a horrible part of town.
Well, then.
You order through bulletproof glass. I'm not kidding. You order through bulletproof glass. And they actually installed a drive-through for the North Shore people to not have to get out of their cars.
That's advanced.
It's awesome. But I've taken students there before we go and eat inside. That's the experience. So we're gonna have to schedule a field trip now. Is what this is coming down to. By the way, we did cover that floating point stuff. Yeah. I still will omit it from the homework assignment, but I went back and looked at it last night. I'm like, there's no way I skipped that. We sort of haphazardly caught. We did it in decimal, not in binary. So the binary, you would have had to make a connection. But regardless, what was your?
Where is this place?
It is on, what's the corner? Is it 17th and Walnut, is that right? It's west of the interstate.
You're dead.
Yeah, it's not. It's whenever you watch the news and they talk about shootings, it's within 2 blocks of that place.
Whenever you start going west off of 93 or whatever it is.
Yeah, I would say probably 90% of the shooting deaths in Milwaukee happen within walking distance of Speed Queen. It's so good. So we'll have to.
It's worth getting almost shot for it.
It's not gonna. I mean, with me there, I just look like somebody's pimp. So they just assume.
White
gold chains. Huge bling.
And you just show up with a bunch of white college students.
That's right.
You know something's going down.
That's right. I don't know what's going down, but something. Yeah, we definitely have to go there. It's a barbecue pilgrimage. Then if you want the second best barbecue in town, you go to Ashley's Q, which is national. Which there's actually a version of Ashley's Q, the original, which is in a dangerous neighborhood too. But then they came out with a safe location. That's more of a college town one. that one, anybody can go to. You'd be fine. So there's your, what's up?
A couple family feet.
I know, they give you a whole loaf of white bread, like in the package that says Wonder Bread, and there's like blood stains on it. Okay, so I don't know how we got talking about barbecue, but no, we were talking about lines of places. Crazy line of cops, that's right. Okay, so in any case, that's why we need the head and tail to keep track of the beginning and end of the line so we can control a queue efficiently. Okay, good enough. So when we are in here in our process scheduler, and we're working with the jobs, when we're working with the ready queue and the device queue, these two guys, we'll be adding to the end, removing from the front. So we're going to take advantage of the fact that Java's linked list already very likely uses heads and tails to add and remove efficiently. Okay? So we didn't have to write that. But if you haven't had 300 yet, when you get into 300, you're going to have to write these from scratch. So you got to pretend like you didn't learn this yet.
Hold on. They offer catering. You can get it here.
It's not fun. Yeah. Part of the experience is going there, eating there, and surviving.
I couldn't survive a night with Evan without having to go to the hospital, so...
Well, if I've probably eaten in Speed Queen 50 times, and I've never had a problem. I think this is one of those things that... No, I don't think so. That's a whole nother layer of danger.
Speed sounds like a washing machine.
Well, and Abe, if you look it up, I don't even know. They've been the #1 barbecue place in Milwaukee since they started rating food places.
It's because everyone's too afraid to actually go there. Oh, we'll just give it #1 again.
There's always a line for the drive-thru like around the corner. It's the place is super popular and super dangerous.
What's the right? People actually go in?
Most don't. Like I said, there's bars in the windows and the door, and you see this giant padlock on the door, and when you go in, you are literally ordering through bulletproof glass. It's so good.
It's really funny because they have bars on the picture on their website.
Love that place. Haven't been in a while. Definitely have to plan a trip. So stay after class for a few minutes if you're interested in this kind of pilgrimage.
It says enjoy and God bless on their website.
I think that's called last rites. All right. So, all right, shut up. We gotta get through this. Come on, people, focus. Gotta focus. I know. So am I. All right. So this is again our process scheduler. So we have our ready queue. We enter the CPU. From the CPU, we can either be done. So a PCB finishes and just leaves the whole process scheduler, no longer part of the job queue. So if you think about what might happen over here, it's going to leave the PCBs. Well, it's already out of the ready queue because it was in the CPU. It was never in the device queue, at least not recently, and it still is in the jobs queue. But as that process finishes, it's going to also leave the jobs queue. So there's going to have to be a signal or a request sent back to the process scheduler saying, I have finished, you no longer have to keep track of me. Does that make sense? This guy needs to be aware, otherwise you get a whole bunch of processes stuck in the system. So we don't want the process scheduler to have to manage any more stuff than necessary. And we also don't want to leave jobs under the control of the process scheduler when those jobs have actually left the system. Because now the process scheduler is going to try to schedule those jobs that don't even exist. And that's when you get things like the blue screen of death and stuff like that on old Windows machines. That would be an example of something that might cause a blue screen of death. The process scheduler tries to give the CPU a job that doesn't exist. All of a sudden we start asking that job for its current state of its registers, and we get null pointer exceptions from a Java perspective, but you're asking a question of something that's not there. All right, so some jobs will leave the CPU and they're done. Other ones will get interrupted from the CPU for whatever reason. They might go into I/O requests. They might go into a time slice expired thing, which We're not, I see Evan just immediately looks over at Abe as soon as he sees the word fork. Is that it? Is that what happened? Well, at least you were paying attention. Okay. I'll take it. All right. So for our example here, we're going to either deal with I/O requests or this idea of a time slice expired. We can throw a whole bunch of different things in there. We're going to say it's time with the CPU is done. Whether we're doing this on a number of cycles, whether we're doing this in an amount of time, whatever it is, it's expired its time on the CPU, and we're going to follow this line and jump back into the ready queue. Make sense? Okay, so we're not going to, in our simulation, deal with forking children.
Did you make this chart, or was this pre-made?
It's pre-made.
You think you would spend that much time making something like this?
Well, if it has the words fork a child in a box.
Now, here's the funniest part of this. Is he has maintained a stoic presence the entire class until right there. And at that point, he lost it. Oh my gosh, people.
And then you wait for someone to interrupt you?
You execute the child.
Bad.
You can't pay for this level of entertainment.
Actually, we can.
Now, I think all of us can agree that your tuition just became a more value-sensitive. You're not going to get this level of stuff at other colleges. All right.
I'm just saying, it looks like you probably made this chart.
No, I honestly didn't. Well, I may have. I would say I would have put dinosaurs on a chart I made, but I probably would not have given credit to. Okay, so remember, we're using the dinosaur book, the kind of the de facto operating systems book. The main reason I use their slide set for this is this really is the de facto book. I would say if you looked at operating systems courses around the country, at least 90% of them use this book. One of the versions of it. It's a really expensive book. That's why I didn't have you get it. But we're at least going to use their data. Okay? I think I probably recommended day one of class, if you wanted to get the book, get an older version.
Or just download it online.
Yeah, you could do that too, but I'm not going to officially recommend that.
Unrecorded.
Doesn't matter, we get the end payment out of what we want.
But you could probably get an older version off eBay, like the 2009 for $10 or something. It's not very expensive. But if you want to buy the latest, greatest version that comes out every year, because these guys are just making bank, it's probably a $140 book or something. About the same price as the math books. All right, so in any case, we're not going to be simulating this aspect of the chart or this one. So we're going to keep our scheduling simple. We're either going to leave the CPU for good, we're going to leave the CPU and wait for an I/O request, or we're going to leave the CPU and go and get back in line for the CPU. Because we're still ready for CPU time. Our time just expired. Okay? So that's what we're going to simulate here. So the part that we haven't written yet is this idea of a CPU. So let's start writing some code for that. So our process scheduler is going to live here. Well, actually, even before we do that, every single time a new job is created, that is, every single time you double click on a program, the process scheduler needs to be made aware. Okay? So let's actually write some ability into our process scheduler for this. All right, so we're going to say, well, let's do this. So we're going to have start process. Now, down the line, we're probably going to take in a string path or something like that. The path of the program that you double clicked on. So C:\\, whatever, blah, blah, blah. And then the start process would go to that path, specifically load that program into memory and do all that stuff. For us, we're just simulating this, so starting a process just means creating a random PCB. Okay, so create a random PCB. So we'll go ahead and do that. So we're going to say PCB, new PCB is equal to a new PCB. And our constructor for PCB takes no parameters and does all the magic for us, right? Right, so there's our PCB. Now, we know that 100% of the time that PCB needs to enter the jobs queue. Okay, so this is to start a process initially. Okay, so 100% of the time we're going to say the jobs dot add. Is there an add last? Yep, add last. That way we're putting it at the end, removing it from the front, so we'll just explicitly call those methods. So the jobs add last new PCB. All right, so now it's been put onto the list of jobs the process scheduler is in charge of managing. Next, we know it's going to get into the ready queue the first time through, right? It needs to at least execute its first line of code, which might be an IO request. But so we're going to say the ready queue dot oh, is that 3s or 4? Dot add last new PCB, and we're not going to do anything with the device queue right now. Okay, so this is how a new process is born. Okay, and it's added to the appropriate queues. Okay, now we're going to go ahead and create our CPU so we can kind of grow that at the same time. So we'll create a new class called CPU. Okay, now we think about the CPU. Let's go back to our picture here. This guy right here, at any point in time, what things is the CPU managing? Well, the CPU is going to be working on a single PCB. That's who currently has access to that resource. And in our simulation, our CPUs are single core CPUs. Okay? For what we're going to kind of write. We'll talk about it at a multi-core level for some examples, but for what we're actually going to write, we're just simulating a single core. So this is a single CPU, a single resource that every PCB is fighting for. Okay? So at any point in time, you're going to have the PCB that currently has access to the CPU, and then you're going to have the PCB that is getting ready to get added to the CPU. Make sense? So when the CPU first starts, it will not have a current process. We'll just say that as our example. So we're going to have a private cur PCB. That's a private PCB, cur PCB. And then we'll make a public constructor for CPU. I'll have this guy take no parameters. In the future, you might have it taken the number of cores, but for ours, we're assuming a 1. Cur's PCB will start off as null. We do not have anything currently in the PCB, or currently in the cur PCB. All right, so now the CPU is going to have a couple of functions. One function is going to be start PCB, right? So we're going to have, with this public, start PCB. This will take in a PCB, the PCB. If this dot cur PCB is equal to null, if there's not something currently in the PCB, then we'll set this dot cur PCB equal to the PCB, and then do whatever needs to be done to start. We'll come back to that. Otherwise, there is something currently in the CPU. So we need to execute a context switch. Context switch cur PCB out. Context switch the PCB in. Realistically here, we probably are going to need to context switch the PCB in, even in that case. That initial time in, it's somewhat of a wasted time, but we may not know, at least in our simulation right now, we don't know whether this is the first time this PCB has been on the CPU, or it's its 20th time it's been on the CPU. More importantly, the CPU currently has its registers potentially set up from the last PCB. So we don't want this guy taking over with registers that already have crap in it. So at the very least, we want to reinitialize the registers on the CPU. Okay? So always best to just go ahead and take that context switch and give it a clean slate. Take a couple of CPU cycles, but the number of times we're going to be context switching, one extra, not a big deal. All right. So we're going to have to think about, what does it mean to context switch? Well, let's go back to our PCB. Process state has nothing to do with the CPU, right? That's not something that the CPU needs to be concerned about. Everything that's running on the CPU has a process state of running. Does the CPU care about the program counter? Yeah, it needs to know where to start, right? But there's going to be a transition between the process scheduler and the CPU that's going to work through the code associated with the PCB, starting with program counter and incrementing that program counter. So the CPU is going to be incrementing that program counter. So we are going to need to know about this in the CPU, but the CPU will directly manipulate that through the PCB. The CPU doesn't need to keep track of its own copy of the program counter. It knows the PCB it's currently working on. It can update it in that PCB. Realistically, it probably does throw it into a register so that it can increment it quickly, but for our simulation, it doesn't keep track of it twice. All right. Actually, in our simulation, it probably should keep track of it twice and then write it back as part of the context switch. So we're going to steal that, go into our CPU, and our CPU is going to have a private long program counter. And let's call this cur program counter. So this is going to be a hardware variable that's going to be holding on to the current program counter. So this guy is going to be involved in the context switch, which means that when we're switching something out of the CPU, we're going to write the cur program counter back into the cur PCB so that it knows where to pick up next time. Similarly, well, we have the code, but we're not going to load the entirety of the code into the CPU at once. We're going to load in one instruction at a time. Deal with that instruction, grab the next instruction. Realistically, in a hardware type class, we would deal with something called pipelining, which is how do we kind of stage the next instructions for the CPU such that they get into the CPU as quickly as possible, so that the CPU doesn't work on one instruction, then go back and do the entire request process for the next instruction. The instructions are kind of in this hardware-based staging area, so it's very, very quick to load the next instruction into the CPU. And while the CPU is working on that instruction, we add one more instruction into the pipeline. Okay? We're just going to call that a segue that is happening in our simulation. All right? Instructions get to the CPU somehow. So we're not going to be concerned about the code right now in terms of its entirety, but we are going to have to keep track of the cur instruction. So when we load the next instruction from the PCB into the CPU, that's going to get loaded into another piece of hardware register, another hardware-based variable in the PCB, or in the CPU, where we will execute the current instruction from that. We're going to be interpreting that based on the 3 different kinds of instructions we supported in our PCB. An IO instruction, which will immediately cause an interrupt. A move instruction, which will cause us to load something into one of our registers. And another move instruction, which will cause us to load something from a register into another register. All right, so we're supporting 3 different things. So the CPU needs to know about the current instruction it needs to parse, it needs to execute. It also needs to know about the current state of all the registers for this particular PCB. Okay? Now, when I say the current state, in this case, the CPU is going to keep track of the actual registers. These are the physical registers, and during a context switch, we'll copy the contents of those registers back into the PCB so that when it gets into the end of the line, it has everything it needs to pick up where it left off next time. Okay, so from an object-oriented perspective, when we think about our CPU, a CPU is going to know about the current PCB it's working on. It's going to know about the current program counter for that PCB. It's going to know about the instruction it's currently working on, and then it's going to know about all of its own registers. Make sense? It's going to know about all of its own registers. Okay, so back to starting our PCB. When we notice that there isn't currently a PCB in our CPU, we'll go ahead and set the cur PCB to that guy. We can do that immediately because we're not having to transition a dude out. But then we need to context switch the PCB into the CPU. So we're going to have a public void context switch in. And this guy will take in a PCB as a parameter, and we're going to add this PCB into the CPU. Okay? That means set the CPU's current program counter equal to whatever this guy's current program counter is. Set this guy's current instruction. Actually, we won't do the current instruction yet. That'll be part of the start idea. But set the CPU's registers equal to the current state of the registers as this PCB knows about them. All right, so we go back to our PCB, and we need to now give ourselves the ability. Actually, we sort of kind of already have the ability, so let's fix our code a little bit. We're going to make all these guys private, just because that's what the cool kids do. It's good programming practice. So all these variables are only accessible inside of PCB. So we won't let somebody externally change the process state unless we allow them to. Okay, now we're going to write setters and getters for these guys so that we can get the process state, we can get the program counter, we can get we'll actually probably get the next line of code, get the line of code at program counter. So we won't just give them the entirety of the code. Nobody needs that. And we're going to get the current state of the registers. All right, so let's just write our getters first. Let me actually just minimize this part. So we'll write a public Right now, we just need program counter and the register, so we'll only expose those right now. Public long get program counter, and this guy will return this dot program counter. All right, so I kind of like software to grow as we go through it, so I'm only going to expose the aspects of it that we need right now. If we need to add some more abilities to it later, we will. So I need to be able to get the program counter from this guy, and I also need to be able to get the registers. Okay, so these are getters or accessor methods that allow us to access a private member of a class. So now I've got the ability to request from a PCB for it to give me its current program counter and for it to give me the current state of its registers. Now back in our CPU, we're going to have, for a context switch, we're going to say, well, this is a context switch in. We're going to say this dot current program counter is equal to the PCB dot get program counter. And then we need to copy from our registers. So we're going to say integer array temp registers is equal to the PCB dot get the registers. Then for int I is equal to 0, I is less than this dot the registers dot length I plus plus. So we'll spin through all of, and you know, if this makes you feel better, we can say temp registers here. They'll be synonyms since our CPU has 4 registers and our PCBs know that the CPU has 4 registers. So those two guys have the same length. So for each of our temp registers, copy into our current set of registers the value. So this is asking our PCB for its remembered register values. Then let's spin through all those register values and copy them into the current registers for our CPU. So our CPU can start its execution. Make sense? All right, I'm going to add a little comment here for us to look at next time. Otherwise, we're done. So we need to write context switch out on Friday. Make sense? So we always want to context switch something out of the CPU before we context switch something into the CPU, unless it's the first time we're doing it. First time we're doing it, we have nothing to context switch out. But from that point forward, always context switch out before we context switch in, otherwise you're going to be overwriting crap. All right, I will see everybody on Friday.